We continue now the discussion of the theory of stationary stochastic processes by focusing now on the air process. We are going to do it with the AR1 process to keep it simple. So an AR1 process is a process that makes a variable YT depend on past values of itself. So an AR1 process makes the variable just depend on the variable the last period, the last time, t minus 1. And we're going to have in the model a constant parameter alpha that we will have to estimate. So the process is represented by an equation like this, and WT is white noise. So these are independent, identically distributed observations. That means there is no correlation between YT and YT minus K for any K. The expected value of WT is 0, and it has a constant variance for every T that is equal to sigma squared. So this is an AR1 process. The expectation of this process using the expectation operator is just going to be using the properties of the expectation operator, particularly, in particular the linear property, linearity property is the alpha E of YT minus 1 plus 0. So since we are assuming that the WTs are equal to 0 and each iteration of this YT minus 1 is going to be YT minus 1 is alpha YT minus 2 and so on, we are going to end up with expected value of YT equals 0. The variance of YT, which we're going to denote by gamma 0, is obviously alpha squared variance of YT minus 1 plus the variance of the WT, which is sigma squared. So we are going to do something kind of strange here. We're going to say, well, this is alpha squared, right? Variance of a constant times a random variable is the constant square times the variance of the variable. So, but the variance of the variable is going to be this, right? We are going to be calling it, it's the same time series, right? The variance of YT is the same as the variance of YT minus 1 and the variance of YT minus 2. So it's going to be also gamma 0 and plus the variance of the random term. So this operation implies that the covariance at lag 0, which is the variance, equals sigma squared over 1 minus alpha squared, just by solving for gamma 0 in this expression here on the left. So as you can see, it's a little more convoluted to find the variances and the covariances of the AR process than the variance and covariances of the MA process. So notice that to avoid having an infinite variance, we require that the alpha squared has to be less than 1, right? We cannot have a negative variance, right? So if the variance equals to 1, if this alpha squared equals to 1, not the variance, the alpha squared equals 1, this denominator will be 0 and then the variance will be infinity. So in order to have stationarity, we have to have some kind of constraint on the alpha, okay? So in general, the covariance is going to be the expectation of YT minus 0 times YT minus K minus 0, right? Because that's the expectation for YT. And it's going to be alpha, right? It's going to be represented, or we could show it, is described in many books, and I'll give you a reference to learn how to do it iteratively, repeatedly, to obtain this relationship that gamma K is always going to be related to gamma K minus 1. So it depends on past autocorrelations. And this coefficient here actually is going to be raised to the K. I have a little typo here. This coefficient should be alpha to the K. Okay, so notice mostly the dependence on past autocorrelations. And that's going to be a big issue in autoregressive processes that is going to require that we use the partial autocorrelation. So let's look into that. Notice this autocorrelation process, which has coefficient 0.9. right? The alpha is equal to 0.9. The ACF, this is a pretty high autocorrelate alpha, right? 0.9. So the series has an autocorrelation function that is dying away slowly. Okay, so it doesn't quite look like the ACF of a non-stationary time series because the process is not stationary. But air processes have the danger that if the coefficient here is 1, the process is not stationary if the alpha is 1. So they could become non-stationary depending on the value of the coefficient. And that's why the ACF looks pretty slow, dies away very slowly if the coefficient goes very close to 1. Okay, so here's another one from the same process that has the same alpha coefficient, but looks very, very different from the previous one. Again, these are all simulations. They're manifestations of the ensemble. Each series is randomly drawn from that model, right? From the ensemble is one. Every time you simulate it, you get a different one, right? Again, you see this is dying away, okay? So the idea is how can we figure out this is just order 1? I mean, you're not, if we just pay attention to the autocorrelations in the autocorrelation function, we're going to end up doing a very long model, very big model, right? Here we have our little r, the sample autocorrelation coefficient up to at least like 15. Are you going to fit a model that has 15 coefficients? Autoregression model with 15? No, this is an AR1 model. It has only one coefficient, right? So the idea is that when dealing with an AR process, we're going to need something else, okay? We're going to need the partial autocorrelation function to identify a model. Okay, these are both AR1, and the ACF leads us to believe that we need a proof. We need to like the variable with yt minus 15, yt minus 1, yt minus 2, yt minus 3, and so on, a very big model, but that's not the case, okay? So how can we tell, how can we view, how can we get a feeling for the theoretical autocorrelation function of air processes with just simulation, right? Theoretically, it's very easy to see because we can just draw it by hand, but we don't want to be doing that. How do we do it with simulation? Well, if you simulate a large number of observations of the time series, you're getting closer to what an ensemble is, right? It's an infinite sequences that could manifest themselves in many different time series. Well, if you do that, and here I simulated 10,000, you don't see anything in the time series, right? Because it's too much data to see anything. But you can see the ACF clearly. And notice how, as we increase the coefficient value, the alpha, they are all AR1s in this column, time series. As we increase the value of the coefficient, the ACF becomes even more and more like the ACF of a non-stationary process. It dies away slowly. It dies away slowly either way, right? But it dies away faster if the coefficient is smaller, and it's slower if the coefficient gets bigger. They are all AR1 processes. We cannot distinguish from the ACF that this is an AR1. What is going to help us? Look at the PACF on the very right column. All of the PACFs have only one significant partial autocorrelation coefficient. So that is true of every AR1, regardless of their coefficient, or regardless of the coefficient, you're only going to see one significant autocorrelation, partial autocorrelation. So whereas you can see many different patterns here, low decaying patterns in an AR1 process, depending on the value of the alpha, the PACF is not going to lie to you, okay? So in the case of the AR1, you're going to need to look at the PACF very clearly, very carefully. And of course, this is 10,000 observations. When you have just 100, you're going to have the noise in the PACF, like we have the noise in the ACF, confusing you and thinking there is something else. The noisy patterns that we observe because of sampling, finite sampling, and shorter time series, you need to also train your eyes to ignore it, okay? As you can see, these models, the MA has a clear pattern, the AR1 has a clear pattern, and you have to train your eyes. And since we want to have models that are small, we want to figure out what's going on in these ACFs and PACFs to try to make our models very small instead of just paying attention to everything we observe because we have a small number of observations, okay? So we see two things in an AR. The ACF dies away at a slower rate as the alpha increases. The PACF tells us the order of the model either way, whether alpha is small or large. And we learn about the order using the PACF, okay? So these are very important lessons to keep in mind. And I just have one last observation. In future modeling, we need to keep in mind that the MA processes are always going to be stationary. The AR processes could be non-stationary, right? If the AR coefficient in the AR1 becomes 1, then we have a problem. We have non-stationary time series. So ARs could become non-stationary. And this becomes harder to see when the processes are AR2 or MA2, right? But MA always, MA1, MA2, MA3 would always be stationary. AR processes, not always, okay? But they have other properties that we'll start study later, okay? So in future lessons, we're going to practice modeling different time series to get familiar with the identification process and other steps already defined, and doing modeling and forecasting. So I'm going to conclude these last 3 videos that I have provided. It's the same lesson, but I split it in 3 parts. By summarizing, we show theoretically, we're not in this lesson, that a process is that showing that a process is stationary requires that we remember our expectation operator, our variances and covariances from probability. And we saw that using those probability concepts, we could show how to calculate the theoretical expected value, the variance, the covariance, the correlation function of 2 very simple stochastic processes, the MA1 and AR1. But we are always hoping when we are modeling that we'll end up with small models like this. And a lot of variables are just AR1s and MA1s. So keep an eye for those. And we have shown 2 examples, right? One example, sorry that sentence is cut. One example showing a non-stationary time process, and another example we showed a stationary process. So you need to know how to do these derivations for different examples. And we have seen only stochastic process for order 1, as we said. But we have noticed something, that they're very different in their autocorrelation structure. Whereas the MA1 has significant autocorrelation, just like 1, the AR1 can have many significant autocorrelations, and the partial autocorrelation function becomes important in this case of the AR1. So I hope you enjoyed this very brief tour in 3 short videos of the theoretical stationary stochastic processes and the kind of calculations we do using our probability to show that they are indeed stationary or not stationary. Little bit of practice will give you a feeling for it. And I hope you have enjoyed seeing the differences between a simple MA1 and an AR1.